10-8, geometric probability. Before we can talk about what geometric probability is, we have to try to remember, how do you find the probability of something happening? If you think back to earlier math classes that you've had, you've done this with examples that involve flipping a coin, choosing a card out of a deck of cards, rolling a die. In all of those cases, and even the other problems that I didn't even mention, to find the probability of whatever specific event it was that you were working for, you took the number of favorable outcomes and divided by the number of possible outcomes. Now we're going to use that same idea when we go into finding geometric probability, but now in geometric probability, we're not going to be talking about picking a card or flipping a coin or anything like that. Now we're going to use models that have points that represent favorable outcomes and total outcomes. So it's all about the point, where could it land, and so forth. So when we're finding geometric probability, what makes it geometric probability is that we're going to use lengths, we're going to use areas, eventually we'll use volumes, and we're going to compare those favorable lengths, areas, and volumes to the entire length, area, or volume. Now the key with this is you have to use lengths with lengths, areas with areas, and volumes with volumes. You're never going to compare a favorable length to an entire area or an area with a volume or anything like that. Okay, it always has to be the same type of measurement that you are using for your favorable value and for your entire or possible value. So the first way that we can talk about this is using a number line and dealing with the length idea. So if we are going to select a point on this segment AB at random, what is the probability that the point that we select is on segment CD? So the way that we're going to write this out is we're going to show the probability being a capital P, and then in the parentheses, we're going to put the event that we're trying to find the probability of. So in this case, I can just write the name of the segment that I'm trying to figure out what is the probability of a point being a part of that segment. So now when I go, excuse me, when I go to actually calculate the probability, I have to put the length of the favorable segment, which is that CD, that's where I want it to the point to occur, over the total possible length, which is the entire length of segment AB. So now we use our picture that we're given, this number line. The length of CD is just 4, from 4 to 8. And the length of AB from 0 to 10 is 10. So now there's 3 ways that you could give an answer for probability. So we're just going to review those right now. First one is just having it be a simplified or reduced fraction. The second possible way you could give an answer for probability is as a decimal. And then the third is as a percent. Now, I might ask for a specific form of the answer, and I may not. If I don't ask for a specific form, you could give it to me in any of these 3. And then, of course, if I do ask for a specific form, make sure you use that specific form. So another example of a probability problem that would be a length problem is when it deals with time. So if we have a bus that runs every 25 minutes and you arrive at the bus stop at a random time, what's the probability you have to wait at least 10 minutes? So this is a length problem. Time is a linear unit. So here I've made a number line that starts at 0 and goes to 25. That represents the bus running every 25 minutes. If I want to know the probability of waiting at least 10 minutes, I look on my number line, and if 0 is when the bus leaves and 25 is when it shows back up, which is what it means to run every 25 minutes. If I'm going to wait at least 10 minutes, that means 10 minutes or more. That means I could be waiting anywhere between that 0 number on my number line and the 15. Okay, the 15 would be exactly 10 minutes. Any of those other points to the left of that 15 would be more than 10 minutes. So the probability of my wait time being greater than or equal to 10 minutes is a shorthand way that you could write it. The favorable portion or length on this number line is 15, from 0 to 15. The possible length would be from 0 to 25, that entire number line. So now I just have to reduce, and this would give me a probability of 3/5. Now, I didn't specify which way we were going to give our answer, so we're just going to leave it as that fraction answer for now. For number 6, we're going to use the same information from number 5. So we have the same bus running every 25 minutes. Now we want the probability we have to wait no more than 10 minutes for the bus. So again, we would start with our 25-minute number line. Now, if we want to wait no more than 10 minutes for the bus, that means we're finding the probability of anything less than or equal to 10 minutes, which would fall onto the number line between 15 to 25, and it would include the number 15, because that would be your exactly 10-minute wait. So now the length of that favorable section, which I have outlined in red, is 10. The length of the entire thing is again 25, which means this probability would be 2/5. Now, it is important that you understand with probability, there's another way to find this second answer. If I want to wait, let me back up a second. Since I'm just dealing with two possibilities, in this case, we're either going to wait for 10 minutes or less, or we're going to wait for 10 minutes or more. There's no other option. Everything would fall into those two categories. Another way we could find this second answer would be to subtract the probability from number 5 from 1. 1 is the largest probability that you could possibly have. It's 100%. Something's going to happen 100% of the time. That's as big as it can get. We would be able to take that 1 and subtract the probability of waiting at least 10 minutes, and that would give us the probability of waiting no more than 10 minutes. Again, since these are the only two possibilities in this case, we're able to do that, and that's what's called finding the complement. That is a term that is used with probability in math. Now, one that actually involves some area. Here we have a dartboard. Any dart that we throw, we're going to assume is going to land in that 1-foot square, which you see in gray on your screen. And it's equally likely to land anywhere on the board. It's important that that information is given so that we know it's not some sort of unfair or rigged game. So our job is to find the probability of hitting the blue, yellow, and red regions individually. And then it gives us the radii of these concentric circles are 1, 2, and 3 inches respectively. So what this tells me is that, first of all, I've got a lot of information I need to put into my diagram. And I do need to notice that I have a 1-foot square, but my radii of my circles are given in inches. So we do need to make sure we look out for that, and we notice we have to have the same units. So when I label my diagram, notice I've changed the length of the two sides of the square from 1 foot to be 12 inches. So everything is in the same units. Once you have your picture labeled, you could go about this a couple of different ways. Some people would do what I've kind of laid out right now is finding all the different areas that I'm going to need first and then calculating each of the what's the word I'm looking for? Probabilities, sorry. Or some people would maybe start setting up probabilities and then use that to help guide them with the different pieces of information that they need to find. You can do it which way makes most sense to you. I don't want to say you have to do it one way or the other. In the end, we all are going to end up having the same work. We're all going to end up, hopefully, having the same correct answers. So for me, I might start out looking at this, in this case, to find all the different areas that I'm going to need. If I have to find probability of hitting the blue area, the yellow area, and the red area, I know I'm going to have to find those 3 areas. And then probability, I always have to find the total possible area. So that tells me I have to find the area of the square. So let's start there. Area of a square. Area of a square, we have a formula, side squared. If we plug in the 12 inches, you would find that 12 squared is 144. I don't have to label this right now necessarily. I could if I wanted to. I could call that square inches. But really the answer is the one that has to be labeled. As you do your work, you may or may not choose to put those labels down. Now, if I want to find the area of the blue circle, I know that area of a circle is pi r squared. Blue circle, I'm told, has a radius of 1 inch. So when I plug that in and simplify, keeping it in terms of pi, again, to keep our answers as exact as possible, I would just have pi for the area of that blue circle. Now, if I want to find the area of the yellow region, which I'm going to refer to as the yellow ring, I have to think about how would I do that. I know I would have to find the area of the yellow circle. So imagine again, if I could peel off that blue circle and see an entire yellow circle behind it, that's one area I have to find. And then I'm going to subtract the area of the blue circle, which we already have. So to find the area of that yellow circle, I know I have to use pi r squared. Notice here I've already plugged in the area of the blue circle. There's no sense in calculating that again if I already have it, especially since it's an exact value. So that yellow circle has a radius of 2 inches. So I plug that in for the r. Gets me to the point where I have 4 pi minus pi. And if I simplify that, again, keeping it in terms of pi so that it's exact, the yellow ring would have an area of 3 pi square inches. Whether you label it or not, it still is square inches. Now, the last area that we have to find is the area of that red ring. That red ring, I could find the area by taking the area of that red circle and subtracting the area of that yellow circle. So here we see that we're taking the area of the red circle and subtracting the area of the yellow circle. Again, area of a circle's formula is pi r squared, and then we have that yellow area, area of the yellow circle that we already calculated up here. So we don't have to find that again. We could just use that value that we already have. So now that red circle has a radius of 3 inches. So if we plug that in and then simplify, we would be able to work our way to find that the red ring has an area of 5 pi square inches. Now that I have all the information, all the different areas that we need, we can start actually calculating the probability. So if we want to find the probability of landing in the blue circle, what we have to do is we have to take the area of that blue circle and divide that by the area of the square. So that's, again, the favorable area over the total possible area. That's why I have pi over 144 already plugged in here. Now, if you take your calculator and divide that, before you put an answer down, we are going to use percentages as our answers for this. And when we do percentages, just like when we do decimals, we want these rounded to the nearest thousandth. So on your calculator right now, you should be looking at a value as a decimal. Before you do anything else, go ahead and multiply that by 100, which is how you are converting from decimal to a percent. And then that value you need to round to the nearest thousandth as your percent answer, and you should have 2.182%. In order to find the probability of landing in that yellow region, or what I have referred to as the yellow ring, we have to take the area of that yellow ring, and we have to divide it by the area of the square. So the values that we would have would be 3 pi over 144. If you want to be safe, might not be the worst thing to put parentheses around that numerator, around the 3 pi. And then again, when you're using your calculator, make sure you take 3 pi and divide it by 144, but don't round it yet. Go ahead and multiply it by 100, and then round to the nearest thousandth. Hopefully you found the probability of landing in the yellow region is 6.545%. Go ahead and calculate the probability of landing in that red region to the nearest thousandth of a percent on your own. In order to find the probability of landing in the red, we have to find the area of the red ring divided by the area of the square. So that means we're going to use our calculators, take 5 pi and divide it by 144. And again, as a percent to the nearest thousandth, that would be 10.908%. Now, we've covered this concept before, but this brings it back around again. If we take that blue circle and we make some changes to that blue circle, how does the probability of hitting that blue circle change? So let's say, for example, we double the radius of that blue circle. So it goes from being a 1-inch radius to a 2-inch radius. What happens to that area? What have we talked about in the past? That we should know now how doubling a linear length affects area. Hopefully you can recall that that area would be called quadrupled. It would be multiplied by 4 times bigger. Now, what does that do to the probability of landing in that area? That probability would also be 4 times greater or multiplied by 4. So instead of your 2.182%, you would be at 8.727%, assuming we hadn't rounded before we multiplied by that 4. So now, what would happen to the probability if you triple the radius? Again, think about this. What happens to the area if you triple the radius? The area is 9 times larger. So what does that do to the probability? It does the exact same thing. It takes that probability and makes it 9 times larger. It multiplies it by 9. Again, a very important concept. If you change a length by a certain factor, how does that affect the area? Very important that you understand that. Last thing we're going to do is we're actually going to jump down to number 10 on your notes. Here we're throwing a dart, and it is equally likely to land at any point in the regular octagon. Notice I have that highlighted. That is very important information. Find the probability of that dart landing in the shaded area. So notice we have shaded areas, we have unshaded areas. But again, the key I mentioned here is that we have a regular octagon. Why is that so important? Well, if it's a regular octagon, we know that all those triangles are congruent to each other because these are all diameters of that regular octagon. So it splits it into 8 congruent isosceles triangles. Well, if all of those are congruent, there's actually no need for us to find the area of all that shaded region. We could simply go ahead and say that the probability would be 3/8 or 0.375 or 37.5%. The key again, regular polygons, we know all those triangles that it would be split into are congruent, so that makes us able to be a little bit more efficient instead of actually having to calculate the work. So if you ever run across a problem like that, it's a good thing to be able to recognize so that you can maybe devote that time elsewhere instead of actually trying to calculate those areas.